Hello friends, this video on System of Particles and Rotational Motion part 19 is brought to you by examfear.com. No more fear from exam. We will now talk about a very important topic that is known as moment of inertia. So far, we have almost covered many of the rotational analogues of different quantities. For example, the rotational analog of force, the rotational analog of linear velocity, linear acceleration, linear momentum, right? So all those things we have already covered. So now there is another important quantity which is left to be discussed for rotational motion. So that is moment of inertia. So let us see, moment of inertia is rotational analog of which quantity? So it is the rotational analog of mass. Interesting, right? So why is moment of inertia an analog of mass? How do we know that moment of inertia is a rotational analog of mass? What exactly is moment of inertia? So we will discuss everything in detail one by one. Now please concentrate nicely on this topic because this is a very important section of this lesson, right? So now we know that in order to know that why moment of inertia is considered as a rotational analog of mass, let us try to write down the equation for kinetic energy in case of linear motion. So what is the equation for kinetic energy in translational motion? So in translational motion, kinetic energy is given as half mv square, where m is the mass of the object and v is the velocity with which the object is moving. So now we will try to deduce an expression for kinetic energy in case of rotational motion. Let us consider any rotating rigid body, right? So now we know that this rotating rigid body consists of several particles, some particle here, some particle there. So there are so many particles inside this rigid body, right? So let us suppose this is the axis of rotation for this body. Now let us consider any particle, say P. So this particle will be moving in a circular path in this manner, where this would be the radius of the circle. Now what will be the linear velocity of this particle? It will be tangential, right? I told about that relationship between v, that is linear velocity, and the angular velocity omega, that is v is equal to r omega. So for a rotating body, we can say that Vi is equal to Ri omega, because this thing is true for any particle which is present inside this rigid body, right? So we can say that Vi is equal to Ri omega. Now what is the kinetic energy? Kinetic energy is half Mi Vi square. So this I can write it as half Mi. Instead of Vi, I can write it as Ri square omega square, right? Now, for a pure rotational motion, in this case we are considering a pure rotational motion about a fixed axis. Therefore, omega is constant in this case. So, omega is same for all the particles. Therefore, we can say the total kinetic energy involved during this rotational motion is sum of the kinetic energies of each particle, where I is equal to 1 to n. So, this will be summation of half mi Ri square omega square, right? So therefore we can say that kinetic energy is equal to half omega square summation of mi Ri square. So this is the expression which we get for kinetic energy in case of a pure rotational motion. So now if you compare this expression of kinetic energy with this expression of kinetic energy in case of translational motion, what do you see? Both have half. This has v square, this has omega square. So the rotational analog of linear velocity v is omega. So that is fine. Now here you have m. So whatever is left out here, that has to be the rotational analog of mass, right? So this shows that summation of mi Ri square is defined as moment of inertia. So we define moment of inertia as summation of mi Ri square, and this is the rotational analog of mass in linear motion. So we write kinetic energy as half I omega square. So this is how we define rotational kinetic energy. So from this we proved that moment of inertia is the rotational analog of mass. Right? Okay. Now let us look at a few points related to moment of inertia. It is always denoted by a capital I. It is defined as I is equal to summation of mi/ri square. That means moment of inertia is defined as the sum of the product of the mass and the square of the distance of each of the particles constituting the rigid body. It is independent of the magnitude of angular velocity, because see, if you can clearly see from this expression that moment of inertia depends on two things. One is the mass of each particle and the second is the radius of each particle, that is the position vector of each particle. So it has nothing to do with the magnitude of the angular velocity omega. It depends on the axis of rotation. However, even though it does not depend upon angular velocity, but it depends upon the axis of rotation. So as the axis of rotation keeps changing, the value of moment of inertia also keeps changing. Now how, that we will see in the next few slides. In next few slides, I'll show you how the value of moment of inertia changes when we change our axis of rotation. Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.